Hey everyone, welcome to our last topic for equilibrium. We're going to go through this idea of a solubility equilibrium. And so there's a little bit of reference in your textbook just to go through to get a few of the tables and concepts, and you'll have those tables if you need them on any assessments later on or anything. So the solubility product constant is where we're going to start, and it's similar in setup in the idea of our KEQ equation from our previous topic or previous unit. So ionic compounds differ in their solubilities and the idea that they are soluble in water. And so most salts of the alkali metals, remember alkalis are group 1 metals, they're soluble in water for the most part. And then there's many ionic compounds that are insoluble. And so this little chart that's here outlines for us the solubilities of ionic compounds when they're dissolved in water. And so it's on page 561, it's table 18.1 in your book. And if you can't see the chart that's here, I encourage you just kind of flip that open because that'll be referenced a bit as we kind of go through these slides. So just kind of going through so we kind of have an understanding of what the table says or what it looks like. It says if we have a compound that is a salt of group 1A, so a metal and ammonia. Okay, salts of group 1A, metals and ammonia. So in this case, it says they're all soluble with the exception of some lithium compounds. So our group 1A metals, all the way down through those, say that they're soluble except that there's some lithium compounds that are not soluble. And so when we take a look at each of the charts, remember that really what we're finding here is that we have different compounds that if it says that they're soluble, then that means that they're going to dissolve in water. And if they're not soluble or insoluble, then they're likely going to make a precipitate. They're going to be something that won't dissolve in water and will tend to form this solid structure as a result. So we can kind of follow along with the different ones here, ethanoates, nitrates, chlorates, and perchlorates. It says that for the most part they're soluble with very few exceptions. If we run into sulfates, sulfates are soluble except if we have compounds that are lead sulfates or silver sulfates, mercury, barium, strontium, and calcium. And so that just gives kind of some examples where, for the most part, these sulfates are soluble, but here's a list of conditions where they're insoluble, where they'll form a precipitate. And then you can kind of read through the list where we have chlorides and bromides and iodides, compounds of silver and some compounds of mercury and lead make them insoluble with the idea that they'd form a precipitate. So just kind of, you don't have to memorize the chart or anything like that, you'll have that for later, but just understanding how it works is a good starting point for this. So next part is just to go through with this understanding. Most insoluble salts will actually dissolve to some extent in water. We've been dealing a lot with these equilibrium reactions. And so they're actually partially soluble. And as an example for this, we can take silver chloride. And so if we go back and look at our chart for silver chloride from before, here's our chlorides. It says they're soluble with some compounds of Ag or silver and then some compounds of mercury and lead. So silver chloride falls in this insoluble part, so it would form a precipitate. And so that's why it's listed as a solid here once it's put in. Now, it says most of them will actually dissolve to some extent in water. And so some of this will break apart into silver ions and chloride ions, but there's this equilibrium reaction where it's going to kind of find a sweet spot. And there's very few compounds that when you dissolve them in water that they're 100% one way or the other. And from what we've been talking about in this unit is understanding that they'll form ions and have this equilibrium value that will make products as well as reverting back to reactants. So a very small amount of silver chloride actually dissolves in water. And so there's not a lot here in terms of what's being dissolved because it's insoluble for the most part. It's going to stay as a precipitate. So we can also write this as an equilibrium expression as well. So we use this idea from KEQ from before, where we take our products and they place them on the top, and then our reactants are on the bottom. So after that, As long as some undissolved AgCl is present, then the concentration of AgCl is constant. We have this equilibrium balance. So remember, equilibrium just means that it's a kind of constant reaction that's always making products, and those products are always reforming into the reactants that they came from. And basically, once it hits a set concentration and everybody's kind of happy in terms of the rate that they're making products and making reactants, then this thing is considered balanced, or it's considered at equilibrium. So the concentration of AgCl can then be combined with the equilibrium constant to form this new constant, this new idea, and it just builds off the other one. So basically what this is, and it's not meant to be overwhelming, KEQ times AgCl, all we did was just go up from our original equation here, one that we knew from before, and we just multiplied by AgCl on the top on both sides. So AgCl effectively just moved over to there, over to our left-hand side. So AgCl times KEQ would equal the concentration product of our two ions. And so that's all that happened here. KEQ times AgCl is equal to AgCl, Ag ions and Cl ions, or silver ions and chloride ions, and then we come up with this new concentration value. This solubility product constant is called KSP, and all that is, KSP just multiplies the two ions together. So KSP equals the product of the concentrations of the ions, each raised to a power similar to the KEQ equation. So similar to KEQ, we get a value that has no units. And the smaller the numerical value of KSP, the lower the solubility of the compound. So the higher it is, that's likely it's going to stay as a precipitate. So these solubility product constants are kind of set at room temperature at 25 degrees Celsius. They do change based on temperature, but for the most part, all the questions you're going to get for this unit is all going to be at room temperature unless you're told otherwise. So all of these are written in scientific notation, so just kind of keep in mind that when you see them, the value 1.8 times 10 to the negative 10, it just tells you how many spots to jump the decimal. So in this case, 1.8 just says we're going to move the decimal 10 places to the left because it's a negative. If it were a positive, we would move it to the right, but all the values on our table are negative values. And so it just gives you different solubility product constants for a few different compounds. And we can see AgCl here at 1.8 times 10 to the negative 10. So they're really small values. So as an example, what is the concentration of lead ions and chromate ions in a saturated lead chromate solution? So